Welcome, my dear students, to the new chapter of our fluid mechanics series, that is fluid dynamics. So it is your module 3. So in the previous chapter, that is fluid kinematics, we studied the velocity and acceleration at a point in a fluid flow without taking consideration the forces causing the flow. So we were not taking the forces which are causing the flow, but in this chapter we will include the study of forces causing the fluid flow. Okay, thus the dynamics of fluid flow or fluid dynamics is the branch of science that deals with the motion of fluid considering the forces causing the motion. So in the last chapter we were not considering, but in this chapter we are considering the forces causing the motion. Fine. So this is the study is called as the fluid dynamics. So the dynamic behavior of the fluid flow is analyzed by the Newton's second law of motion, which relates the acceleration with the forces. So the dynamic behavior of the fluid flow is analyzed by Newton's second law of motion. So I hope you remember the Newton's second law of motion. What is that? Yes, my dear students. So it is the rate of change of momentum is directly proportional to the impressed force and takes place in the same direction in which the force acts. Correct? So it is nothing but what? Newton's second law, that is force is proportional to mass into acceleration we have studied. So from the Newton's second law we are getting these equations, right? Okay, so now this fluid is assumed to be incompressible and non-viscous. Here we will assume the fluid to be incompressible and non-viscous. Okay, if the fluid is assumed to be incompressible, so what are the criteria? If it is non-viscous, what are the criteria? We already studied in the fluid kinematics part. So it will be analyzed in this chapter. Okay, now we will see one by one. So what are the theory part of this chapter, and for the problematic part we will do another video. Okay, so according to the Newton's second law of motion, the net force Fx acting on a fluid element in the direction of x is equal to the mass m of the fluid element multiplied by the acceleration in the x direction. Okay, what they are telling, the force acting on the fluid element in the direction of x is equal to what? Mass into acceleration. So mathematically what we can tell, that Fx is equal to max. So where x is the telling it is in the direction. Okay, if it is in the x direction, then we have to take the force and we have to calculate the acceleration in the direction of the force. If it is force is in this direction, Fy, then Fy is equal to m into a into y, and it's depends upon the direction of force, that is force is like this or like this. Okay, now in the fluid flow the following forces are present. So what are the types of forces? So there are 5 types of forces. Okay, that is in on that Fx is what? The net force. So net force means it's a total. So in that how many force are there? So it is comprising of these 5 forces. Okay, what is that? Gravity force, pressure force, force due to viscosity, force due to turbulence, and force due to compressibility. So ಇವೆಲ್ಲ ಫೋರ್ಸಸ್ ಸೇರಿ ಆಗ ಫೋರ್ಸ್ ಏನಂತ ಹೇಳ್ತೀವಿ? Fx. So Fx is what? The net force ಅಂತ ಕರಿಬಹುದು. Okay, so I am writing from the mouse, so please adjust the handwriting. Okay, so Fx is equal to m into a, where m is what? Mass of the fluid, a is acceleration in the direction of flow. So this Fx is what? It is comprising of this gravity force, pressure force, force due to viscosity, force due to turbulence, force due to compressibility. Okay, so now, so from the equation, now what is the equation? Fx equal to, that is, F is equal to m into a, right? So this Fx is what? Net force. So in this, Fx is comprising what? F of Fgx, Fpx, Fvx, Ftx and Fcx. Okay, if the force due to compressibility, if the force due to compressibility, if the force is due to compressibility, then Fc is 0. Okay, then what is the resulting force? The resulting force F is comprising of only gravity force, pressure force, viscosity force and turbulent force. So such equations of motions are called as what? Reynolds equations of motion. The force in the net force, if compressibility is 0, then that equation of motions for that fluid, particular type of fluid, we will call it as Reynolds equations of motion. Suppose if Ft is negligible, for the flow turbulence, Ft is negligible, the resulting equation of motions are called as what? Navier-Stokes equation. Okay, remember it. If the flow is assumed to be ideal, okay, if the flow is assumed to be ideal, then Fv, viscous force, is 0, then the equation of motions are called as what? Euler's equations of motion. Okay, if the flow is ideal, viscous force is 0. So that only they assumed in our first slide. That is, flow is assumed to be incompressible and also non-viscous. Okay. So if the flow is assumed to be ideal, viscous force Fv is 0 and equations of motions are known as Euler's equation of motion. Now we will see what is this Euler's equations of motion. Okay, we will derive the formula for Euler's equations of motion. So Euler's equations of motion. So this is the equation of motion in which forces due to gravity and pressures are taken into consideration. The forces due to gravity and pressures are taken into consideration. Here we derive by considering the motion of fluid element along a streamline. So considering a streamline in which flow is taking place in S direction, we will consider a streamline in which the flow is taking place in S direction as shown in figure. So I'll show you the figure. So we will take a cylindrical element of cross section dA and length ds. Okay, so the cylindrical element we will consider as cylindrical element. So we have to derive an equation now. So we'll assume a cylindrical element, cross section dA, area, okay, length ds. So I'll show you the figure now. So the forces acting on the cylindrical element are, okay, so this is the cylindrical element. Okay, the forces is acting in the direction of S. See here, the force is in this direction. Yes, fine. So this is the forces on the fluid. Okay, now we should know what are these forces. So on this fluid element, in the direction of flow, pressure is acting. Okay, so this pressure force we will take it in the direction of flow, that is P into dA. Okay, so because of this force, another force opposite to that will also act due to Newton's third law, correct? So that is nothing but this one, P plus dou P by dou S into ds into dA. Okay, so the length of the cylindrical element is ds. Okay, area is dA. Okay, so the pressure force acting here, it is what? P into dA. Okay, and the pressure force acting on this face, it is what? It is varying up to ds. Okay, it is varying as length, right? It is varying linearly, so that's why we are taking partial function of what? P plus, so some addition force due to the length of the element, that is dou P by dou S into ds. So this is the pressure force acting on this face into what? The area dA. Here also P into dA, here also P into dA, but here this is due to the length of the cylindrical element. Okay, so in the direction of flow, so see the direction of flow is like this side. Okay, so in the direction of flow only we will take as positive, and opposite to the direction of flow we will take it as negative. And also here theta is there, see. Okay, so before theta, so this weight of the element is what? This one, rho into g dA into ds. Okay, rho g is what? It is telling the weight of the element. So weight of the cylindrical element is, so rho into g into dA into ds is the weight of the element. So the angle between this weight of the element and the direction of flow is called as what? Theta. Okay, I'll clear all the annotations. Okay, this is called as theta. So it is the angle between what? Direction of flow and the line of action of weight of the element. So what are the three forces acting on the cylindrical element? First force is what? Pressure force PdA in the direction of flow. Next one is pressure force P plus dou P by dou S into ds into dA opposite to the direction of flow. Next is weight of the element rho g dA into ds, that is towards the gravity. Okay. Next what? Theta is the angle between the direction of flow and the line of action of weight of the element. Okay, this is the setup of the cylindrical element. Okay, now what we have to do? So we will take the resultant force on the fluid element. Okay, here the resultant force on the fluid element in the direction of flow. Okay, in the resultant flow of this fluid element in the direction of S. So here the flow is in the direction of S, right? Okay, the resultant should be equal to what? Mass into acceleration. So that is your Newton's second law is telling us. So this resultant force, whatever the resultant force we are getting, it is equal to what? Mass into mass of the cylindrical element into acceleration in the direction of flow as. Okay, so what we have to find now? We have to find the resultant force on the cylindrical element. So in the direction of flow only we will take. So what is the resultant force? So first one we can take it as P into dA. So we'll take in the direction of flow, it is as positive. Okay, P into dA, so it is negative, right? So minus this one. Okay, so minus P plus dou P by dou S into ds into dA. Then which force is acting? Weight is also acting. So I'll take as weight, that is this term as here weight of the fluid element. Okay, which is equal to, okay, the forces in the direction of flow, thus the resultant force is equal to what? Mass of the fluid element, okay, into acceleration of the fluid element in the direction of S. So what is mass? If we neglect g, or if we divide the weight by g, this is the mass, that is rho into dA into ds, okay, into as. So what is this acceleration? So as is what? As is nothing but rate of change of velocity dv by dt, correct? But here v, the velocity v is the function of s and also the time t. Okay, so I'll show you in the slide one by one. Okay, why I shown you here only? Because by looking at the diagram only you can derive the formula. Okay, so how the force is going to act, so what we need to apply, okay, step by step like that. So after I'll show you. So this here the resultant force on the fluid element in the direction of S, wait, in the direction of S must be equal to the mass of fluid into acceleration in the direction S. Okay, So what? The resultant force PdA minus this force P plus dou P by dou S into ds into dA minus weight. Okay, rho g dA into ds cos theta. Why? So it is taken as theta. So in the direction of flow we want, right? Okay. So in the weight is this weight is pointing towards downwards, right? So we want this weight to be shifted here. So what we can do? So it is nothing but W cos theta. Okay. So this is rho g dA into ds into cos theta. Okay. Is which is equal to what? The weight, mass into acceleration. Okay, clear? So where as is what? Acceleration in the direction of s. But what is as? So it is nothing but the rate of change of velocity, where v is the function of s and t. Okay, so in the mathematics, whenever x is a function of y and z, how we are partially differentiating it? Same way we have to differentiate here, that is dv by dt. How we are taking? Dou v by dou s into dou s by dou t plus dou v by dou t. So once it is cancelled, we are getting the same, that is dou v by dv by dt, like that. Okay, it's a concept of mathematics. Okay, so since what happens? So dou v by dou s into ds by dt plus dou v by dou t is equal to what? This dou s ds by dou t, space distance by time. So distance by time is what? Velocity only. So v into, so I'll take this as what? V. So v into dou v by dou s plus dou v by dou t is what? Your as. So acceleration is equal to what? This one, v, that is a dou v by dou s plus dou v by dou t. Correct? Suppose if the flow is steady flow, okay, the flow through this cylindrical element is steady flow, then for steady flow dou v by dou t is what? This is 0. Then the acceleration, the direction of s is equal to what? V into dou v by dou s. Okay, so that is the next point. If the flow is steady, then s is what? V into dou v by dou s. Okay, so now substituting this value in the equation 6.2, that is resultant force, which we have find out here. No, so this is the, right, so this is the resultant force. Here we have to substitute the value of as. Okay, so once, how to substitute? We have to first multiply this. When we multiply pda minus p into dA plus dou p by dou s into dA, this p into dA and this p into dA get cancels. Okay, minus dou p by dou s into ds. So simple substitution is there. Okay, simple substitution, and we have to calculate. So we will get what? See here, substituting the value of as. Okay, simplify, and then after simplification, what we are getting? Minus dou p by dou s into ds into dA minus rho g into dA into ds cos theta, this is weight, is equal to mass into what is this? As dou v by dou s. Okay, now what we are doing? We are dividing this by rho ds into dA. So once we divide this by rho ds into dA, we are getting this equation, that is dou p by rho dou s minus g cos theta is equal to v into dv by dou s. Okay, so once we get this value, after rearranging we will get this value, that is dou p by rho into dou s plus g cos theta plus v into dv by ds is equal to 0. Okay, just don't listen, try to note down, you will get connection with the steps. Okay, when you connect the steps, you will get to know the essence of what the formula is. Okay, so once we get this formula, that is dou p by rho into ds plus g cos theta plus v into dou v by dou h is equal to 0. So what we can substitute? We can substitute this cos theta. So what is this cos theta here in this element? So cos theta is what? We can write this cos theta as dz by ds, correct? So cos theta can be written as dz by ds. So I'll substitute this. So from figure 6.1b, we have cos theta is equal to what? Dz by ds. So once we substitute that, we are getting what? 1 by rho dou p by dou s plus g into dz by ds plus vdv divided by ds is equal to 0, or dou p by dp by rho plus g into dz plus vdv is equal to 0. So just rearranging, we can write as dou p by p plus g dz plus vdv is equal to 0. So this is known as our Euler's equations of motion. So we have to remember this formula. So what is Euler's equation of motion? dp by rho plus g into dz plus v into dv is equal to 0. So this is known as our Euler's equation. So next we will see the next equation, that is Bernoulli's equation from Euler's equation. So now we are aware of the Euler's equation. So what is this Euler's equation? That is dp by p dp by rho plus g dz plus vdv is equal to constant, right? So this is your what? Euler's equation. So how we will obtain the Bernoulli's equation? Just by integrating it. Okay, if we integrate each term of Euler's equation, we are obtaining what? Bernoulli's equation. Okay, so what is that? Integration of dp by rho plus integration of g dz integration of vdv is equal to constant. But here in the Bernoulli's equation, we have to we have also one condition, that is if the flow is incompressible. So I already told you, when the flow is incompressible, so what is constant? Rho is constant. Okay, so if the rho is constant, then what happens? This rho is constant, right? So what we can tell, this integration differentiation cancels, integration differentiation cancels, integration, and also this differentiation cancels. So what we can expect, that is integration, after integration, this p, okay, is p by rho, because rho is constant. Okay, it is not it will not come in the integration term. Okay, plus what we can write, g into integration of z, dz is what? Z. Okay, integration of dou p is p, integration of dz is z, plus integration of v, that is v into dv, so same term. So v integration, what will happen? V square integration of dv is by 2, v square by 2. Okay, with respect to dv, no, same term, v square by 2, okay, is equal to constant. So this term I was telling you. So once, if the flow is incompressible, rho is constant, we are getting p by rho plus g z plus v square by 2 as constant. Okay, now if that is constant, by rearranging the terms, what we can write? So p by rho g dividing by g, okay, p by rho g plus z plus v square by 2g is equal to constant. Okay, so we can write in this fashion, that is p by rho g plus v square by 2g plus z is equal to constant. So this is what this term is called, the Bernoulli's equation. Okay, this is also very important formula in this chapter, Euler's equation and also Bernoulli's equation. P by rho g plus v square by 2g plus z is equal to constant. Here each and every term has a significance. So this P by rho g is called as what? Pressure energy. Okay, pressure energy. This v square by 2g is called as what? Kinetic energy. Okay, kinetic energy. and Z is called as what? Potential energy. Okay, are all equal to constant. Okay, so here in this equation, this P by rho G is the pressure energy per unit weight of the fluid, or pressure head, we can tell as pressure head. V square by 2G is what? Kinetic energy per unit weight, that is kinetic head. Z is what? Potential energy per unit weight, or potential head. Okay, we can call this as this potential head, kinetic head, and it is pressure head. It should be constant so that the Bernoulli's equation is valid. So now we got to know the equations of the Bernoulli's equation. Okay, ಆ equation ಏನು ಅನ್ನೋದು ಗೊತ್ತಾಯ್ತು. So equation satisfy ಆಗಬೇಕಂದ್ರೆ, if we want to satisfy the equation, what are the assumptions? Okay, so in the exam they will ask what are the assumptions made in the derivation of the Bernoulli's equation. So I'll tell you the assumptions now. So assumptions made in Bernoulli's equations are: the fluid is ideal, that is viscosity is 0. The flow is steady. So whatever the Euler's equation, whenever I derive the Euler's equation, whatever the conditions I took, no same conditions. Okay, the flow is incompressible. Yes, in the Bernoulli's equation, the flow is incompressible and the flow is irrotational. It should not flow through its axis. Okay, the flow is ideal. So only 4 points. What are the assumptions? The fluid is ideal, the fluid is steady, the flow is incompressible, the flow is irrotational. So these are the assumptions made in the derivation of the Bernoulli's equation. So once we know the assumptions, how can we state the limitations? Okay, assumptions ಗೊತ್ತಾದ್ಮೇಲೆ limitations ನಾವು ಹೇಳ್ಬೋದಾ? Okay, here ಇಲ್ಲೇನಿದೆ, the fluid is ideal, the viscosity must be 0 ಅಂತಿದೆ. So viscosity 0 ಇದ್ದ ಮಾತ್ರಕ್ಕೆ, so the fluid which have 0 viscosity, that type of fluid is only valid for this Bernoulli's equation. So one limitations, the flow is steady. So on each and every point we can create the limitation points. So I'll tell you, I'll discuss now. So what are the limitations? So this theorem is applicable for Newtonian fluids and hence cannot be used for non-Newtonian fluids. Okay, so what are these Newtonian fluids? I already discussed with you. And this theorem doesn't take viscosity into account. So first assumption. Okay, and hence viscous fluid cannot be considered applicable for this theorem. Bernoulli's theorem is applicable only for streamline flow, hence cannot be used during the turbulent flow when the Reynolds number is greater than 2000. Okay, the fluid has to be incompressible. Okay, the fluid to what? To assess or to make valid the Bernoulli's equation, the fluid has to be what? Incompressible. Hence its density cannot change with time or pressure. So these are the limitations of what? The Bernoulli's equation. Okay, same assumption. If you know assumptions, you can tell, you can write in your own words the limitations also. So this was about the Bernoulli's equations from Euler's equation. So it was for ideal fluid. So what will be the Bernoulli's equation for a real fluid? Okay, so in the practical way we are encountering what? The real fluid only. Okay, so the Bernoulli's equations were derived on the assumption that the fluid is non-viscous, it is inviscid, and therefore it is frictionless because it's ideal fluid now. So the Bernoulli's equations were derived on the assumption that fluid is non-viscous and therefore frictionless, but all the real fluids are viscous and hence offer resistance to the flow. But ವಾಸ್ತವದಲ್ಲಿ ಏನಾಗುತ್ತೆ? Real fluids are viscous and also offer the resistance to flow. Thus there are also always some losses in the fluid flow. Because of this resistance, there are always some losses in the fluid flow. Hence in the application of the Bernoulli's equation, these losses have to be taken into consideration. Whenever we will apply the Bernoulli's equation, we have to consider some of the losses which are applying in the system. So what is the equation happen? What will be the modification in the equation? I'll let you know now. So this is also called as what? Modified Bernoulli's equation. So Bernoulli's equation for real fluid is also called as what? Modified Bernoulli's equation. So this is the formula. Thus, the Bernoulli's equation for real fluids between point 1 and 2 is given as, between point 1 and 2 is, if we take this system, okay, where a fluid is flowing, I'll take this as point 1 and this is point 2. Okay, so at this point 1, P1 by rho g plus V1, what is the P1 by rho g plus V1 square by 2g plus Z1, which is equal to P2 by rho g plus V2 square by 2g plus Z2 plus HL. So this HL is what? Head loss. Okay, so what is this P1 by rho g? I already told you, pressure head. This is kinetic head. This is potential head at section 1-1. So this is pressure head, kinetic head, datum head or potential head at 2-2 with some losses. So this HL is called as the loss of energy between the point 1 and 2. So hence this is called as what? Modified Bernoulli's equation, that is P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2 plus HL. So here I conclude my lecture on this fluid dynamics. In the next chapter or in the next video, we will see some of the problems or the theory part, so that we can finish it faster, and we will go one by one covering the syllabus. So thank you. So if you want any notes or manuals related to our VTU syllabus, you can just come or log into my Telegram group, so that the materials are easily available to you. Thank you. Have a good day.